and share with friends. So with that, I am pleased to hand things over to Dr. Eusden, who's a professor of geology at Bates College.
Hey, thanks, Nora. Thank you for that. And hi, everyone. You're seeing me from my little hole in Carnegie Science Building in Eusden, Maine, on the campus of Bates College. I would do the Zoom from home, but my internet at home is so terrible. I have to come into Bates to have the right bandwidth. So here we go. Let me just jump in and share my screen, and we'll go from there. And Nora, let me know if you can't see or hear anything, but it should be okay, right? Okay. Yeah, I recognize a few of the names on the Zoom call tonight. It's great to see everybody and spend maybe an hour or so getting to know a little bit better the geology in the White Mountains, and especially with a focus on the Presidential Range. And if you saw my talk in 2019, some of this will be a repeat, but I've added some things that we've done since 2019 as far as adding parts of our research. But I wanted to look at the geology of the whites through the lens of three different minerals: magnetite, to look at the plate movements over time, and andalusite, which is a mineral in the schists up on the high peaks in the Prezes, that can tell us how tall the mountains were, and apatite, and some Fission Track method we've used on those to determine when the topography formed in the White Mountains. So that's the plan. And I thought I'd start with a really brief general overview of things like, the rock cycle, geologic time, and an overview of tectonic boundaries. So that's the plan. See if I can figure out how to advance the slide. There we go. Okay, so my research has been mostly in the White Mountains, although I do some in the Maine coast as well. But we've published a couple books. The most recent one is the one in the upper left on the geology of New Hampshire's White Mountains. And I've also published one on the geology of the Presidential Range with a nice map on the back that you can take up on the mountain with you to investigate the geology on your own time and terms. And I've been continuing my research with the U.S. Geological Survey and both the New Hampshire and Maine Geological Surveys. And this summer, I'm actually working on a project in Western Maine, and you may have heard about it in the news. It's a fairly large deposit of lithium in around the town of Newry and Rumford in Andover, Maine. It may be one of the top 10 biggest lithium deposits in the world. And so, down the road, the folks in Western Maine and probably in New Hampshire are going to have to face the question of, whether we want to mine for lithium, have an open pit mine to harvest that element to make renewable, batteries, rechargeable batteries to support green energy and lower CO2 emissions. So it's going to be a difficult question to answer. Oops, sorry. This shows the index map of all the areas we've worked in the White Mountains. And I'm sure you're familiar with the topographic quad maps. These are the 7.5 minute quad index maps. And I show you this just to piece together the work we've done over the years. So sort of in the pale yellow color and in the light orange, those are quads that either I've mapped with Bates students or other folks have mapped. And in green are quadrangles we're currently working on. The East Andover one in Maine is where the lithium deposit is. And this summer I'll be mapping in the Shelburne area along the Mahoosic range where the Appalachian Trail goes through. So we've put together a pretty good swath of mapping from about the Vermont, New Hampshire border and Lancaster all the way over through New Hampshire into the Western Maine in the area of Bethel. And this is a recent geologic map and the cross section that goes with it. The cross section is, just a slice into the earth along that line on the upper diagram, the map that goes from A to A prime. And it just shows what the geology might be in the subsurface. And, we're putting together lots of different quadrangles and some new geochronology to figure out the age of things. But you can see here's the town of Jefferson. This is Mount Washington here where the cursor is. This is Berlin. And this is Bethel way over here. Here's the New Hampshire, Maine state line. So that's the vicinity of the work we're currently doing. And it sort of shows up as these quadrangle maps. And this is the map on the left is the one we just published last year for the Berlin, New Hampshire quad with the US Geological Survey and the New Hampshire survey. And it shows a big fundamental break in Appalachian tectonics between these rocks sort of in green and purple, which are part of an old volcanic arc, and these rocks in sort of gray and different shades of green, which are part of the sedimentary basin that formed back in the day.
This should.
And this map is the one that shows the lithium deposits. These pink blobs here are the lithium bearing granitic rocks. And what's amazing about them is that you can see in this lower picture on the right, these gigantic crystals of lithium bearing minerals. This is the mineral spodumene. And some of these are like 20 feet long and like 3 or 4 feet across. That's Frank Perham, a famous mineral collector in Western Maine, standing in front of it for scale. Okay, so that's a little bit about the work I've been doing in the Whites and elsewhere. And so let's just start the sort of review part of the talk. And this is the rock cycle. And I'm sure you remember, the three main geologic rock types: sedimentary rock, metamorphic rock, and igneous rock. And what I like about this diagram is it ties them all together by the processes that form one and then form another. So, if you start out up here in the top diagram where it says mountains up on Franconia Ridge, there's rain and wind and snow and lots of cold tonight and freeze thawing eventually. And we're breaking up the rock into particles and we're transporting it as pieces down the river systems into the ocean, where it eventually gets deposited as sediment and turned into hard sedimentary rock. Now, if you take a plate collision and you squeeze those sedimentary rocks, you're going to increase the heat and the pressure, and you're going to turn the sedimentary rock into metamorphic rock. And they might show a change in texture and grain size to go from a shale to like a schist, but they also may show folding and deformation. And that's what you see in this picture from Cragway Corner up on the Mount Washington Auto Road. You could even take that metamorphic process further and start to partially melt the rock, and then you would generate a rock called a gneiss or a migmatite. And the little white blobs in this lower center picture, those are the melted portions of the metamorphic rock. And even further, you could extend that process of increasing the heat and the pressure to completely melt the rock to make a magma. And the magma would be underground. I show you a magma at the surface, a lava, but to give you the idea, but the magma formed in this way by melting a metamorphic rock would be underground. Then we could take that magma and we could erupt it at the surface to make a volcano or a series of volcanoes like this picture on the left, or we could freeze it underground to make an intrusive igneous rock. And the most famous one in New Hampshire, of course, are granites. And all of these rocks, regardless of whether they're sedimentary, metamorphic, or igneous, can be uplifted to form mountains. So, you can uplift a sedimentary rock by tectonic uplift. And indeed, the highest peaks in the world on top of the Himalaya are sedimentary rocks with fossils in them. Similarly, you could uplift metamorphic rocks, and that's what makes up the high peaks in the Presidential Range. And same thing with granitic rocks, you can uplift them to form mountains. Of course, you need to erode rock to expose the granite, but that's easily done. And the extrusive rocks are a little bit different in that they make mountains sort of as they erupt. So they're kind of constructing mountains as they are being born. So there's your crash course in the rock cycle. So now your crash course in geologic time. This diagram's a little bit dated, but I like it because it shows sort of the spiral of geologic time going down to the very bottom, which represents the age of the Earth, 4.6 billion years old, based on ages of meteorites, not so much ages on the planet itself. And then it kind of spirals up to the present. And I show in the red arrows some key times that reflect the geologic history of the White Mountain region. So the Cambrian period, those record the oldest rocks in the White Mountain. That's a formation called the Albi Formation, and it's about 550 million years old. There are older rocks in New Hampshire and Maine, but those are the oldest ones in the White Mountains. And then the arc I mentioned before is called the Bronson Hill Volcanic Arc. That formed in the Ordovician period. And then at the beginning of the Silurian and up to the very early part of the Devonian, there is a period of deposition of sediments in a basin called the Central Maine Basin. And after that, there was widespread deformation and metamorphism as one tectonic collision after another happened, and I'll get into that in a second. And then in the Jurassic and Triassic period, we had the supercontinent Pangaea, but it had to split apart to create the Atlantic Ocean. And during that time frame, we also generated abundant granite intrusions in the White Mountain region, especially around the Conway region. In the Cretaceous period, and I'll talk about that with respect to the mineral apatite, we suspect here is where some of the differential erosion happened between the valleys and the peaks to create the topography of the Presidential Range. And at the very end, in the Quaternary period, we had glaciations and glaciers covering the landscape and creating both glacial erosional features and glacial depositional features. And of course, at the end is the newest period, which isn't on this diagram, called the Anthropocene, which is the period in which human impacts have greatly affected geologic processes. Okay, so that was crash course in time. Now your crash course in tectonics here. So this is a diagram from the Stephen Marshak intro geo textbooks that are used by lots of colleges and universities. And the artist is Hinks. And Hinks does a great job portraying these sort of 3D images, showing all the different plate tectonic boundaries and some that are not tectonic. So we'll start in the center here in the middle of the ocean. And this is a mid-ocean ridge where material, magma, is coming up from the mantle and cooling at the sea floor water interface, and then spreading laterally both left and right, or east and west. And that's creating new ocean crust. So there's magma associated with it and the creation of crust, ocean crust. That ocean crust may move to the left, and it may encounter another ocean crustal plate, and one or the other will go under. And that's a subduction zone or a convergent plate boundary where plates are being destroyed. And what's really interesting about the convergent boundary is that there's magma created above the downgoing slab of ocean crust to create a volcanic arc. And, just in the news this week was that amazingly impressive Tonga eruption that you could see from space. And that happened on one of these tectonic boundaries of a subduction zone and a convergent plate system along a volcanic arc. So not only do ocean plates interact and collide in convergent plate boundaries, but so do continental plates. And that's this diagram in the lower left. And this is where two continental sized plates come together. Neither are very susceptible of subducting. They're lighter, they like to stay up. So they create very wide and very long and very tall mountain belts with a commensurate deep crustal root underneath the highest peaks of the mountains. And then the third type of plate boundary is shown over here, where plates are sliding by each other. There's really no magma associated with this type of plate boundary. And this would be equivalent to like the San Andreas Fault in California or the Alpine Fault in New Zealand. So transform boundaries, mid-ocean ridges, and convergent boundaries of a couple different types. And then there are, non-tectonic boundaries. So this is the case of a Hawaii hotspot where there's a fixed plume of mantle material coming up, punching through the overlying plate. And, I don't know if you can see my hands and my finger, but if this is the plume coming up and the plate's moving over it, it makes a volcano, and then that volcano moves off and it makes a new volcano, and so on and so forth. and the ones away from the plume are inactive now, and the ones on the plume are the active place where volcanism is happening. Okay, so that was like my Geo 101 class in 10 minutes. So we'll just jump into tectonics, and then after tectonics, we'll tackle each of the three minerals, the magnetite, andalusite, and apatite, one by one. So just as an introduction to the Appalachian Mountains, you probably know already they extend from, Georgia, Alabama, all the way through New England into the Canadian Maritime provinces and up through into Newfoundland. And they actually, though, if you were to close up the Atlantic Ocean and reconstruct the ancestral Appalachians before the Atlantic Ocean formed, they actually extend all the way into United Kingdom, Scandinavia, Eastern Greenland, part of France, Spain, and the northwestern coast of Africa. And in fact, some of the best rock equivalents that we have in the White Mountains are found right across in Morocco region. So this is a very extensive mountain belt if you put it back together by closing the Atlantic up. And in terms of the plate that, the White Mountains, and probably most of you right now, I'm not sure about all of you, but most of you are sitting on, is the plate called Gander, or the Gander volcanic arc. And it's shown in this sort of pale orange and the pale green color. And, it's the floor or the basement for the White Mountains. It extends all through Maine and into New Brunswick and Nova Scotia and into Newfoundland, and to the south through New Hampshire, Massachusetts, and Connecticut. And then it kind of dies out and isn't found again after you get to Long Island Sound. And each one of the plates that you see here, whether it's Laurentia, Gander, Avalon, Maguma, were these subsequent collisions that happen one after another to create the Appalachians. Okay, so the first mineral I want to talk about is magnetite. And magnetite is an iron oxide. And what's cool about magnetite is that it preserves the magnetic field in it. And it has a couple components, probably one of them really well, and that's this one, the declination. And the declination is just simply the difference between true north and magnetic north. And the only place where true north and magnetic north are the same are on these green lines. So if you happen to be on a green line, you don't have to adjust your compass at all. But if you live in New England, like most of us do, you're at about minus 10, 12, 14, about minus 16 or 16 degrees west of north. So you would have to adjust your compass to account for that magnetic declination. And this map is a crazy pattern, and I don't honestly understand why the pattern is as it is. It's a very complex magnetic field interaction, I can only imagine. But we know where this map is, we know the declination is, and we can then adjust and correct our compasses for it when we go out and measure things like bearings or rock orientations. The more useful component of the magnetic field for geologists, especially with respect to understanding tectonic histories, is the inclination. And the inclination is the angle that the magnetic needle or field makes with respect to the Earth's surface. And the way the story works, if you look at these little insert diagrams to the right, and this one in the center, this is the magnetic inclination at the equator. So the Earth's surface is shown here with little trees on it, and the needle is parallel to it. And up at the North Pole, the inclination is oriented at 90 degrees to the Earth's surface. In other words, it's pointing straight down at the North Pole, the magnetic North Pole. And it varies systematically between, a needle that's parallel to the Earth's surface to a needle that's oriented 90 degrees. And this map shows the variation. So, in New England, the inclination is about 62.46, about 68 degrees, pointing toward the north. And it, changes direction as you go to the southern hemisphere. And the inclination is just about zero at about the equator, as shown in these diagrams, the inset diagrams. What's useful about the inclination is in the mineral magnetite, when it cools and forms as a mineral, most often in a basaltic rock, the magnetite mineral preserves the magnetic field, both the inclination and the declination. So if you can figure out that magnetic field, you can then determine where on the Earth you might have been in terms of latitude, either northern hemisphere or southern hemisphere. So it's an incredibly useful component to the magnetic field. So here are a couple examples from an intro geotext that shows sort of how this might work. And on the left is just a stack of rocks from 600 million years to zero, or today. And the declination is shown with the compass rose here, and the inclination is shown with the needle on this little stick. And so, you would interpret the rock layer at zero, since it's oriented at almost, vertical to the contact of the sediments. It's nearly vertically oriented, with south pointing down, that this would be near the South Pole. And conversely, if you look at 600 million year layer, you can see the magnetic needle is nearly horizontal. So at 600 million years ago, this layer was deposited near the equator. So that's how you can tease out the paleo latitude and the hemisphere that the plates once existed in. So here's another example that might make it more clear in terms of plate modeling. So here are successive positions of a plate that's moved across the globe. A is the older and D is the more recent. And, the paleo inclination would suggest for position A that it's north of the equator, at B that it's on the equator, at C that it's south of the equator, and D a little farther south. So the bottom line is, with magnetite, we can determine the paleo latitude using the inclination. The only difficult thing is, with that information alone, we don't really know the longitudinal line that the plate might exist on. However, there are some other keys, and I don't really have time to get into this tonight, but these features called large igneous provinces and kimberlites, which are where diamonds are often found, linked to low velocities zones in the Earth's mantle, and they're fixed points like a mantle plume to create the Hawaii hotspot. Those can actually constrain paleolongitude. So these two things together have been really helpful in controlling what we know about the plate positions over time. So this diagram, I know it's a little bit busy, but if you focus on that red lines of arrows connecting each other, so you start up here and you go to here and then here and then here and then here, and we're going to look at the reconstruction of the plate gander or Ganderia over time. So the oldest time snapshot is here in the Cambrian, 510 million years ago, then the Ordovician, 450 million years ago, then the Silurian, then the Devonian, and ending in the Carboniferous 300 million years ago with the formation of Pangaea. So let me just walk you through what happens to poor Gander here over time. So Gander was pulled apart and off of Gondwana back in the Cambrian. And this little line here with the double teeth on it, that shows a mid-ocean ridge, a spreading center that pulled apart Gondwana into fragments. And one of the first fragments to get pulled apart was Gander. And then between the Cambrian and the Ordovician, Gander migrated across this old ancestral ocean called the Iapetus Ocean, and to get close to Laurentia, which is ancestral North America. And I don't know if you can recognize this shape, but that little shape there, that's Hudson's Bay and James Bay, and this is Greenland, just to show some modern day features so you can recognize roughly where things are, even though those didn't exist at that time. These lines with the single teeth on them are subduction zones, like the one in Tonga, and quite an active area at the time. And then in the Silurian, you can see that Gander is now part of Laurentia. It's attached to it. That's one of the first collisions to happen. And another plate, Avalon, this one in orange, has also peeled off of Gondwana, also made its way across the oceans, and is also going to slam into Laurentia. And this particular collision, the one of Avalon with the composite Laurentia, that's the most important one for the deformation and metamorphism in the White Mountain region for the older rocks. And then certainly we have to take Avalon and collide that in with everything else. And this little bit here shown as this kind of olivey green. This is actually a plate called Maguma, which is essentially the geology and the rocks found in Nova Scotia. And then the last thing we have to do is just bring together Laurentia and Gondwana to make the supercontinent Pangaea, and that's done at the beginning of the Carboniferous around 300 million years ago. So if someone were to ask you when the Appalachians were finally formed and at their heyday, the tallest, where would they have been? They would have been right along this line right here. So this would have been the Appalachian Mountain Belt right there. And I know some of you have been staring at these little blue balls for a long time now and have figured out that all these little pluses, these black pluses in the center, that's the South Pole. And these dotted lines are lines of latitude. This is 60 degrees south. This is 30 degrees south. And the outer dotted line, that's the equator. So we're looking at the southern hemisphere. So what that means is that all of these plate interactions to eventually form, the framework for the White Mountains and the Appalachians themselves, all of these interactions happen south of the equator and then eventually made their way north of the equator because we know that's where we are today. And I'll show you how that works in just a second. But that's the sort of path you can get from the paleomagnetism study of magnetite for the plates that make up the Appalachians. Okay, so after Pangaea forms, then we have to rift it apart to create the Atlantic Ocean. And this is a little animation that I'll run for you that shows the plates as they pull apart. And so you'll see down in the lower left, the age 250 MA is millions of years ago, and then the time period and all the plates moves. And this will go up to 60 million years ago. So we'll start it, there's 240. 220, and now you're going to see North America start to rift away from Western Africa. And then after that, you're going to see South America start to rift away from Africa. And then you see over here, this purple blob, that's India, that's going to slam in eventually to Asia to create the Himalayas. And that doesn't happen until 40 million years. So that's the rest of the story of the plate movements after Pangaea. We got close to what it looks like today, but not quite. We're almost there. And a lot of this was done by paleomagnetism too, but also the magnetic reversals in the ocean floors that are recorded so nicely in the Atlantic Ocean and in the Pacific. Okay, so that's the story of magnetite. And let me turn now to the mineral andalusite. If I have a favorite mineral, it's definitely this one. It's an aluminosilicate mineral. And what's unique about it is that it only grows in certain pressure and temperature conditions that can tell us how tall the ancestral presidential range and Appalachian Mountains were. I'm going to first show you this little video, which I think is useful. It's about a 3-minute video, and it shows a sand analog model of mountain building that's really good, and it produces structures, especially folds and faults, that we've seen exact copies of in the field in the presidential range. So let me run this and just yell out, Nora, if you can't hear it.
How do mountains form? We see them in just a moment of time, but they form over millions of years. Mountain belts extend for hundreds, even thousands of kilometers, and their structures penetrate deep into the earth. So their size and age make their formation difficult to understand. French geologist Jacques Malavier builds sand models that mimic the formation of mountain belts and allow scientists to study this complex process.
In order for an experiment that runs for only a few minutes, but represents natural phenomena that happen over many tens of millions of years, we have to choose a material whose deformation behavior does not depend on time. Sand is a very good material for simulating rock deformation. In the experiment, the different stratigraphic layers which represent the sediments and the continental crust have different mechanical properties. We mix the sand grains with a finer powder, which increases the sand's resistance to deformation. Thus, we have heterogeneous material made up of more resistant layers and less resistant layers.
Mountain belts are created when continents collide. In this experiment, we see two continents separated by an ocean. Now watch what happens as the plates converge. As one plate subducts or dives beneath the other, the ocean basin closes. The continental crust, which is lighter than oceanic crust, cannot be subducted. Instead, as the continents collide, the crust thickens and is forced up. Note how the sand is folded and faulted. We see similar structures in the rocks in mountains. One important factor not accounted for in this model is erosion. Erosion exposes the deformed rocks that were once deeply buried in the mountain belt. The green sand represents the rocks of the ocean basin. Note that it's been trapped between the two continents, marking their original boundary. These too we see in mountain belts. It's very difficult to understand the deep structure of a mountain belt by direct observation. The sand model allows us to compress time and space and simulates the internal structure of mountains.
Yeah, so I love that video because it's a nice segue to this cross section, which is one we've drawn from Bretton Woods to the left, over Mount Monroe near Lakes of the Clouds, across the lawn here, Bigelow Lawn, down the head wall of Tux, and down all the way to Pink of Notch. And the geology is shown sort of more brightly colored where it's exposed at the surface and below ground, and above ground in faded colors where it once was but now has been eroded away. And we know that it used to be there based on the projections of these structures in 3 dimensions. And you can just see these gigantic folds that formed in the region. And, you know, this is a cross-sectional scale, so it's a regional scale, but even at the outcrop scale in the field, you can see these folds everywhere. So here's a beautiful fold of a little granite that Bates student Carter Kinley is sitting next to. And here's another fold, very much like the fold you see in the cartoon of the cross-section above on John Quincy Adams, where Maura Foley and Simon Wilbanks were doing their thesis work. And just another one, this is the cross-section we made for our Presidential Range book and the map of the northern Prezzies from Jefferson to Madison, and the Google Earth image below. And you can see, you know, 1, 2, 3, 4, 5 giant folds, you know, with wavelengths on the order of 1 kilometer or 2 that form by the collision of plates and creating these folds, and also creating metamorphism. So during the collision and the formation of these folds, the temperature was increasing and the pressure was beginning to increase. And what happened was that this mineral grew from the sediments that were in the Presidential Range initially, as they became schists. And you've probably all seen this hiking above treeline, this sort of very rough textured rock that often has a sort of aligned crystals. And these are the Andalusite crystals that can only grow if they have the right chemical composition, just the right amount of heat and the correct amount of pressure. What's really interesting about the Andalusite in the Prezzi Range is that it's actually now been replaced by other minerals. So there's this inset here, and in the very center, you can see a core of a fairly white mineral. That's called Seleminite. It's another aluminosilicate. It's surrounded by a rim of muscovite, the clear mica, and then sometimes some amber brown mineral called staurolite. But these crystals that you see in the rock, those used to be the Andalusite, and now they've been replaced by Seleminite and muscovite by successive periods of metamorphism. So it's a very complicated metamorphic story, but it tells a good story, and I'll show you that in the next slide. So, you know, we know that the rocks that make up the Prezi Range were once sediments in an ocean basin. So in this diagram, we're going to plot their path through a graph that has temperature on the x-axis from 0 to about 800 degrees Celsius, and depth, whether you want to look at it in kilometers at the surface down to -20 below the surface kilometers, or miles from at the surface 0 to, down to about 12 miles below the surface. And since the rocks of what's called the Littleton Formation were deposited as sediment, we know they had to start up here in this red dot. They know they were relatively cool. They're on the sea floor as sediments, and they weren't very deep. They're right at the surface. And then as the deformation started and we began to make those big folds, we started to increase the temperature and the pressure. The temperature first, and then the pressure eventually caught up with it. Andalusite only grows if it lies in this blue field. And so we had Andalusite develop as the first folds formed early on in the history of the Presidential Range mountain building. Then as the temperature increased to its maximum, so did pressure, and it got to about 700 degrees Celsius and a depth of about, let's see, that's 5, 6, 7, about 8 miles. So about 8 miles below the surface. And then we also know that since we can walk on these Andalusite schists today, that we had to have these rocks become exposed back at the surface again, preserving all these great structures that we can see and analyze. So there's a couple other peaks of metamorphism that happened, mostly related to granites intruding and or the opening of Pangea and basalt dikes coming in, like the one, at Pinnacle Gully in Huntington's. So the take-home message from this graph is that, we started and finished at the surface, but we went to great depths and high temperatures, depths of about 8 miles below the surface and temperatures of about 700 degrees Celsius. That also means that when the schists were down in here, and to get up here, 8 miles of rock had to have been eroded off of Mount Washington. So if you think about that, these two crustal columns may help you get your head around this issue. So the column on the left is today's continental crustal column. It's about 25 miles thick, based on some really well-constrained geophysical methods that we use to determine that. This is sea level here, the dashed blue line, and the present day topography is about a mile high. If you think of Mount Washington as 6,000 feet and change, and a mile at 5,288. So it's about a mile of topography. If we add back in the 8 miles of rock that was eroded away, that's what gets us to the column on the right. So that's the sort of faded blue. That's the 8 miles of eroded material that's now offshore somewhere in the Atlantic eastern seaboard as sediment. I didn't all contribute to the paleo height of the mountains. About a third of it did. And the way you can think about that is if I took a huge slab of ice and I put it on top of an iceberg, I would actually push the iceberg down into the ocean a little bit. Certainly some of that slab of ice I added would add to a new higher height for the iceberg, but a lot of the ice would actually be pushed down deeper into the ocean. Same thing with crustal blocks being pushed down into the Earth's mantle, which is fluid-like. So the crust back in the day was about 32 miles thick, and the topography from sea level was about 4 miles above sea level. So that translates to mountains the size of like the Rockies or the Andes, maybe 14,000 to 20,000 feet tall. And one tricky way to look at this is you drive over to Lunenburg, Vermont, and you look back east near sunset, take a picture of the Prezis from Mount Washington over to Mount Adams on the far left over here. And that's 1 mile of topography. And then you take it into Photoshop and you stretch it so it becomes to scale 4 miles. And I stretched it only vertically to make the peaks sharper and the ridges steeper, because that's probably what it looked like back in the day when the Prezi Range first formed in the Devonian 400 to 360 million years ago. There's some really great new work that's just come out in the last few months that actually has quantified the thickness of the Appalachian Mountain crust in the New England region. This is work done by a Bates student, Ian Hillenbrand, who did his work at University of Massachusetts Amherst. And in red down here, this is down in Connecticut, parts of Rhode Island, and Western Mass. That represents areas of the crust that were greater than 60 kilometers in thickness, kilometers. And then in this orange yellowy line, this oval, which is about coincident with the White Mountains, this shows areas where the crust was about 60 kilometers thick. So a little bit less, but still really thick. And then in Maine, where I live, this area in green shows crust that's maybe on the order of like about 40 kilometers thick, something like that, 40 to 45. So if you think about that, the thinner the crust, the smaller the mountains, the thicker the crust, the taller the mountains. So Ian in this paper would estimate that in Massachusetts and Connecticut, the mountains were Himalayan Tibetan plateau size, 15,000 to 20,000 feet, maybe even higher in places. In New Hampshire, they're the Rockies or the Alps, so the 10,000 to 15,000. And in Maine, we're, quote unquote, the foothills, 5,000 to 10,000 foot tall mountains. And this is happening along one mountain belt. Back in the day, during the heyday of the Appalachians, there would have been highest peaks in southern New England and lower peaks in Maine. And if you look at a modern day analog of an active mountain belt that's being formed currently, one good place to see transitions in elevation like this are in the Andes. And I just put these two blue lines on this topographic map of the Andes that's contoured in kilometers above sea level to show, possibly a place where you go from really high peaks that are around 20,000 feet into a little less tall peaks that are 15,000 feet into this green, which are like 5,000 foot foothills. And you could, same thing down here, the same transition from high to middle elevations to low elevations. So we see this now in the present day landscape, and and now thanks to Ian's work, have been able to document it in New England. Okay, so the last mineral I want to talk about, and then we'll wrap up, is the mineral apatite. It's a calcium phosphate. And it's a very common mineral in almost every rock, schists, granites, you name it. But what this mineral has allowed us to do is to evaluate when the modern day topography in the Presidential Range and the White Mountain developed. And the way it works is we take advantage of the fact that in apatite, in the crystal chemical formula, is a little bit of uranium that can decay radioactively. And it creates these damage tracks called fission tracks. And you can see it in this photomicrograph of this apatite crystal here. So all these little black lines, these are damage tracks or fission tracks in an apatite crystal. The longer ones are oriented more or less flat. The ones that are just like dots are like, a pencil going in and out of the page like that. And the tracks are interesting because they develop all the time, but they're only preserved in the crystal when it's cooler than 100 degrees Celsius. So if the crystal is here and it's formed and it's now cooling below 100 degrees Celsius here, it's a little cooler, we begin to see some tracks. So that's good. And as the cooling continues and the radioactive decay happens and more tracks form, we develop even more tracks. However, if we heat up the apatite, the tracks will heal or anneal and resorb back into the crystal. So you can have tracks of different lengths in an apatite. And if they're long tracks, that means they cooled really quickly. If they're short tracks, that means they cooled very slowly and stayed sort of hovering around 100 degrees Celsius for a little bit longer time. Okay, so to do this work, this is Bridget Anderson. She's one of the students who was involved in this project. We brushed off the old Kelty and Jansport frame packs, which I don't really use much anymore, but they're really good for carrying lots of rock. And we sampled rocks every 500 vertical feet down the Cog Railroad in Outcrop and also down the Auto Road. And our goal was to see if we could find out more about this area of the geologic timescale where this pink blob is in the Cretaceous, because this is a period for which there are no rocks in the presidential range of that age, and we don't know much about it. But this technique of apatite fission track dating actually can get us some information about the Cretaceous. Okay, so here are the results. So, you count the number of tracks, and the more tracks there are, the older the rock is. The fewer tracks there are, the younger the rock is in terms of its age of cooling below 100 degrees Celsius. And the pattern here turned out, it was just a fantastic pattern. So the Cog Railroad is this white squiggly line, and this is Pinkham Notch, where the Glen House is, and Great Glens, and all the great ski trails over there. And this is the Cog Railroad, this dashed white line going down to the base station and eventually to Fabian's. And what you can see is down in the valley, the ages are younger. They're around 90 to 100 million years at the base. And at the top of the mountain, the ages are older. They're, around 147 up to about 152. So about 150 million years at the summit. And, that makes sense if you think about it, because the valley, which is much lower, was more deeply buried back when these apatite fission tracks were forming. And it took a longer time for it to cool below 100 degrees Celsius. So the ages are younger, whereas the summits, because they were closer to the top of the crust, they cooled a little faster, and they cooled before the valley did at older time periods, about 150 million years ago. So that works out great. But the really important information we got from the apatite fission tracks were the track lengths themselves. And there's a little busy diagram, but let's just walk you through it. So these two plots on the upper right show the track lengths on the Auto Road from the summit and the base. And the track lengths at the base are longer than the track lengths at the summit. And this was also true, exactly the same measurements for the summit and base based on the Cog Railroad transect we did. And so to think about tracks again, in the valleys, the tracks are longer. So that means that they cooled and eroded rapidly. While the tracks in the summit are shorter, that means they partially healed themselves or annealed, and they cooled and eroded much more slowly. So we can model the track length differences between the valleys and the summits to figure out when things eroded differently. And that's what the graph down below shows. And the key panel to focus your energy on is this one in the light blue. So this particular path with the hollow or filled circles, those show the modeling track ages for the summit based on a temperature time plot. And what you can see is that there was rapid cooling early on in the history of the summit, from about 160 to about 120 million years ago. And then from 120 to about 60 million years ago on the summit, it's flatlining, meaning that there's no change in temperature, so there's no cooling, and there's also no erosion. Things just were sitting there. Whereas in the valley, you can see it's another steep curve from about 120 to 60 million years ago, meaning that there was rapid cooling, long tracks, and lots of erosion happening in the valleys, while the summits weren't doing anything. So erosion in the valleys, nothing going on in the summits in this time frame, 120 million years to 60 million years ago in the Cretaceous. So a way to visualize that, that's not sort of in a graph form, but in a cross section, is to draw a cross section from east to west, from Bretton Woods up and over Mount Washington, down to Pinkham, and then up toward the Carter Range. And then you add back in the layers of sediment that have eroded over time. And from about today, this black line, through this green and this sort of blue-green color, up to 60 million years ago, there's been about 1 kilometer of rock eroded off the top, but it eroded equally everywhere. So essentially, what was high 60 million years ago is still high today, and what was low 60 million years ago is still low today, mimicking today's topography. The really interesting time period is from 60 to 120 million years, when we had about 1 kilometer of erosion in the valleys, both in Pinkham Notch and over in Bretton Woods, while the summit had no erosion. And that gets to the Fission Track length story. And in fact, about 120 million years ago, you can see that the summit of Mount Washington would have been about the same height as Pinkham Notch, or Pinkham Notch would have been the same height as the summit of Mount Washington. So the incision was localized to the valleys and left the summits untouched. And this is work we did about 8 years ago, and fairly recently in 2019, Michelle Fame and co-authors did a slightly different study in the same area, and really discovered the same thing using a different method, that there was differential erosion in the Cretaceous that preferentially carved out the valleys and left the summits untouched. So, thinking about that, how do you not erode the summit and erode only the valleys? Well, one way possibly to do that is by having faults in the valleys that weaken the rock. And there is one, the Glen Ellis Fault, that's down on the south end of Pinkham Notch, but there really aren't a lot of other faults, that are similar over on the Bretton Woods side. So though that's a possibility, I don't think it's explains everything. The possibility I like the best at this point is that the ancestral drainages of the Androscoggin River, the Saco River, and the Kinetic River, all of which converge on Mount Washington, may have started to form about 120 million years ago and incised preferentially the valleys, leaving the summits untouched. So that's sort of where we are with this work on apatite fission track ages in the White Mountains, suggesting when the current topography developed sometime between 120 and 60 million years ago. And since 60 million years, there's been very little change in what was high and what was low, although for sure the glaciers have modified the landscape and polished and smoothed it. But the key things were these more long-term processes that happened over tens of millions of years of time. Okay, so let me just recap, and then we can have you folks ask some questions if you'd like. Happy to do that. Nice Brad Washburn picture here showing the mountains from the sort of Oaks Gulf side, looking north toward Mount Washington. And magnetite, because of the two components, declination and inclination, especially inclination, can really help us reconstruct the paleolatitude of plates over time. And that helped us determine that most of the plate interactions to form the Appalachians, and in particular the Presidential Range, were south of the equator and eventually moved to the north as Pangea rifted apart. Andalusite, the aluminosilicate in the schists of the Presidential Range, can tell us how tall the White Mountains were, and their Rocky Mountain size. And the new work that Ian has done has shown that there's quite a variation as you go from southern New England into Maine in terms of the paleo Appalachian mountain heights, from like 20,000 feet to about 5,000 feet from south to north. And the apatite and the fission tracks in them can help us understand, how the later erosion unfolded and the evolution of the topography, especially carving out the valleys in the Cretaceous time period. So that is all I wanted to say. And let me go to this nice view from, probably looks a little bit like that right now over Bretton Woods. And I'd be happy to take your questions, and I'm going to turn it over to Nora. And Nora, what I think I'm going to do is go to my slide sorter mode and keep my screen shared. So if anyone has a particular question about a slide, I can just zoom right in on that.
Great. And Dykstra, thank you so much.
You're welcome.
That we are over here taking notes and trying to wrap our head around all of this. And
you're going to have to watch the video a couple times.
I know. Well, see, there we go. This is one of the reasons. These are those silver linings of having these things recorded. So a couple of questions, one that I had myself and one that came in, and I guess that they're sort of related, going back to the magnetite and the inclination and declination. And that is, I guess the first piece is, what tools are used to, the question that came in, like, basically, how do you measure declination or inclination, or put another way, if someone were to have, if you were to have a piece of a sample of magnetite in front of you, how are these numbers being determined?
So the declination's easy enough. I mean, you can just do that easy with a compass, depending on where you go, and just look at the deflection of the magnetic needle. That's straightforward. The inclination's a tricky one. And what you have to do is you have to drill a core of the basalt rock that has the magnetite in it. And you have to have it oriented, because if you lose its orientation, then you don't know what the magnetic field orientation was with respect to, today's coordinate system. So you can just mark it up with a Sharpie before you drill it, and you pull it out. And then you stick the core in a thing called a spinner magnetometer, which actually spins it and rotates it, twists it, and determines the two components that you're talking about. And, it sounds easy enough to get those two things, but the problem is, like, if the rock has been like tilted or folded, you have to untilt it, you have to unfold it. So the geometry that you have to do once you figure out the inclination and declination in the spinner magnetometer can be quite tricky. And there are elaborate tests now to see whether your unfolding or untilting passes or fails certain tests. And it's often hard to achieve. So the best samples are from rocks that are relatively undeformed, that you can, and that are old, and you can actually drill out a core of basalt to determine the paleomagnetic field.
All right, so not something we are doing at home with
Well, you could, I mean, you can definitely see variations in the magnetic field. There's this great outcrop in Cascoban, this island called Cliff Island, that's made of magnetite. And, if you just take your compass and you like wave it over that rock, you'll see the magnetic needle deflect like 90 degrees. I've never encountered that, up on Mount Washington region, with the exception of the basalt dikes that have magnetite in them. And those can be tricky sometimes to measure, because when you get your compass next to them, there's a little deflection. But you can actually, just a standard run-of-the-mill compass can help you out understanding the declination.
Great. So along those lines, we had another question actually that came in along with a question that my husband had as well.
Yeah, so and this is kind of along with someone asked about. I was curious, one of the graphs you showed had mountains in Connecticut and Massachusetts at 15 to 20,000 feet, White Mountains at 10 to 15,000 feet. And so I was curious if there were ideas as to, because that's a tremendous erosional rate that's taking place in those Connecticut and Massachusetts mountains to bring them down. And I was curious what might account that, if it's like rock type, if it's that erosional, that differential erosion you were talking about, like what's going on that erosional rate is like twofold or threefold as it was in the White Mountains.
Yeah, so I mean, it's probably twofold when you compare it to like Maine, but it's probably maybe a third again more than the White Mountains. But still, it is a lot of rock to remove. And we don't think that there was really any different rock types there to, account for like variations in resistance or not to weathering. So we think it's pretty much all the same kind of continental crust. It just so happened that the collision there was more intense. Like, can you see the slide I have on the slide sorter now in the screen share? Yeah, so this little bend in the Andes created quite a bit of compression and quite a bit of uplift. So something like that must have been going on in the Connecticut region to create the higher topography. It's so counterintuitive now, right? Because you think of the higher peaks, where we are in New Hampshire, right? And then you drive to Connecticut, it's pretty much down to sea level. But nope, the estimates that Ian has done based on some really fantastic geochemical signatures suggests that the crust was indeed that thick. And now everywhere in New England, the crust is about, 35 to 40 kilometers thick. So there has been quite a bit of differential erosion, way more in Connecticut than certainly compared to Maine.
All right. So here's a fun question for you that
Yeah.
in reading who it's from, it does not surprise me. And that is, how well can geological findings predict the future as opposed to describe the past?
Yeah, well, it's kind of a two-way street there, because and it's a good question because most of my research is describing past events, right? But I have to say that when I've done several sabbaticals in New Zealand, right? So that's an active plate boundary where the mountains are growing currently. And the erosional level there would have been like, the Appalachians back 400 million years ago, right? So when the mountains were at their tallest. Now, the New Zealanders know that there's metamorphism going on, but they don't really know too much about the kind of metamorphism and deformation that they would expect. But we Appalachian geologists can tell them, right? So we can actually say, okay, the type of metamorphism and deformation you would be seeing below ground in the New Zealand Alps is what we might see, for example, in the Presidential Range or down in Connecticut and central Massachusetts. So the comparison between active and ancient tectonic regimes is where we can answer that question. So. Yeah, I think I learned more going to New Zealand about the Appalachians than I did about the New Zealand mountains, in terms of like what might have been here in the past, and certainly for them, what they might have below ground that they can't see.
Mm-hmm. So another question about that differential erosion. So this one says, with regard to limited erosion at the peak of Mount Washington compared to surroundings, could the limited watershed area around the peak be a factor in which the surrounding area and three major rivers enveloped a larger rainfall watershed?
Yes, it's possible. I don't know enough about the rainfall sort of cycles in the Cretaceous to answer that question, because that's when this was happening. So in this diagram, this little blue and this red sliver, that's what was taken out of the valleys in the Cretaceous time period from 60 to 120 million years ago. And I don't really understand what the paleo environment was like in terms of the rainfall. Certainly, if you think about today's, catchment basins, yeah, that's reasonable to assume. But I just don't quite know what they were like back then. I was really heartened to see this newer study showed the same thing with a different method. So it's been replicated now actually two times, which is great, by another study out of some folks from Middlebury. So yeah, but a lot of questions there in terms of like what triggered this differential erosion in the valleys only. I mean, I'm throwing out some ideas here, but I think we have a ways to go to sort that out, and a lot more research is needed. But we didn't know anything about the Cretaceous really before, so now we know a lot more, which is good.
All right, so that brings me to the end of the questions that came in through the chat. If anyone has any additional questions that wasn't answered through any of that, if you want to go ahead and type anything in, or if you just want to unmute yourself and ask any questions directly. Otherwise, I think you've all got.
Nora?
Yes, Dana.
Yes, okay. Bob has a question for Dyke. And thank you
Okay.
so much, Dyke, for everything.
Oh, you're welcome.
This presentation was so great. I was a geology major at Harvard in the 40s, and I had Billings. You probably remember Billings with the doctoral students doing all the work on the presidential range of that area.
I
But
sure do. I
what-
sure do.
What
Yeah.
I didn't have I have so many good illustrations here. I had to try and figure these things out from descriptions in books. And these things are now would make it so much easier to do it. Plus, I'm interested in noticing how many of the diagrams that you have used have been done in the 21st century. It shows how much the knowledge about geology has increased.
Yeah, I'll probably be saying something like you're saying in about, 30 years when I hear a talk. So I think the techniques are going to continue to change and improve, which is a good thing. In addition to the recording that Nora is going to provide, which is super helpful, Nora, thanks for doing that. Most of these diagrams are in the White Mountain Geology book that we have published back in 2013. Not all of the new stuff, but most of them. So if you want to take a look at that.
And I think that everyone should know that Dyke has seen the Stella's sea eagle. That's a really exciting thing. And since Bob and I have seen it too, we were delighted to hear that you had got to it.
Yeah, that was a spectacular bird. I thought eagles were big, but bald eagles, but the Stellar's eagle is about a third again as big. So it's pretty amazing. Yeah.
Professor Dykstra has provided us with a link to someone who's been telling us about what has gone on geologically in the Dixville Notch area. And that's been most helpful and most appreciated.
Yeah. No, that's really good information from Professor Wally Bothner down at University of New Hampshire.
All right, Dick, we did have I just had one final question coming.
Sure, yeah.
And probably because they're, seeing those illustrations with Pangea. So early on, you said that Pangea was formed in the Southern Hemisphere. And the question is, was the movement from the Southern Hemisphere to the north because of currents or other reasons?
Yeah, so those movements were, the idea behind the breakup of a supercontinent is that underneath it are some sort of restless mantle plumes that eventually spread it apart. And the orientation of the plumes were such that it pushed, Laurentia and a lot of this real estate actually into the Northern Hemisphere. So these diagrams that on my slide sorter, all these diagrams that start with slide 14 and go to slide, whatever that is, 35, those show the progressive movements of Pangea over time. The only thing that's a little bit confusing about this diagram is they have the latitude and longitude fixed. And I think it's not quite that way. It's actually changing over time. So you'd be looking at a different snapshot of the Earth. But you get the idea that they rifted apart after they formed south of the equator and drifted to their current latitudes, where we are now.
All of the northern things above the equator come from the breakup of Gondwana?
Pangea.
Pangea.
Pangea, yeah. Yeah, everything today on the planet is a product of the breakup of Pangea. And, the idea is that there is a cycle of supercontinent formation, breakup, and then reconfiguration of a new supercontinent, then break up. So we had Gondwana, broke apart, and then came together to form Pangea and broke apart. And that cycle has gone on multiple times in Earth history.
All right, wonderful. Well, thank you so much.
Thank you, Professor.
Thank you for all this information. I will do my best to have this up on our YouTube page sometime tomorrow so that folks can go back and brush up and on all of this, as well as share it.
Great. Well, thank you, Nora. Appreciate it.